Old physics. At every attempt to study the world and nature, we inevitably find ourselves confronted with a series of definite questions to which we are unable to give direct answers. But upon our recognition or non-recognition of these questions, upon our way of formulating them and upon our attitude towards them, depends the whole process of thinking about the world and consequently about ourselves. The most important of these questions are the following. What form has the world? Is the world a chaos or a system? Did the world come into being accidentally, or was it created according to a plan? Strange as it may at first seem, one or other solution of the first question, that of the form of the world, actually determines the possible solution both to the second and to the third questions. If the question as to whether the world is a chaos or a system, whether the world came into being accidentally or was created according to a plan, are solved without being preceded by a definition of the form of the world. If they do not result or arise from such a definition, then those solutions lack weight, demand faith, and fail to satisfy the mind. It is only when the answers to these questions are derived from the definition of the form of the world, that they can be sufficiently exact and complete. In spite of its importance, the question of the form of the world has seldom arisen independently, and is usually included in other problems, cosmogonical, cosmological, astronomical, geometrical, physical and other. The average person would be surprised if they were told that the world might have a form. For them the world has no form. Yet in order to understand the world one must be able to build some model of the universe, however imperfect. Such a model of the world, such a model of the universe, cannot be built without a concept of the form of the universe. To make a model of a house one must know the form of the house, to make a model of an apple, one must know the form of the apple. Therefore, before passing to principles upon which a new model of the universe can be built, we need to examine briefly the history of the question as to the form of the world, the state of this question in science and the models that have thus far been built. The ancient and medieval cosmogonical and cosmological concept of exoteric systems, that alone became known to science, were never very clear or very interesting. Furthermore, the universe they pictured was a very small universe, much smaller than the modern astronomical world, so we can therefore leave them to posterity. A study of different views of the question concerning the form of the world can begin from the moment when astronomical and physiomechanical systems freed themselves from the idea that the Earth is the center of the world. The period in question embraces several centuries, however we can confine our research to a period commencing from the end of the first quarter of the 19th century. By that time, the sciences that studied the world of nature had long been divided, and stood then in the same relation to one another in which they stand now, or stood at any rate until quite recently. Physics studied phenomena in matter around us. Astronomy studied the movements of celestial bodies. Chemistry endeavored to penetrate the mystery of their structure, and the composition of matter. These three physical sciences based their concepts of the form of the world entirely upon the geometry of Euclid. Geometrical space was taken as physical space. No difference was distinguished between them, and space was taken apart from matter, just as a box and its capacity may be examined independently of its contents. Space was understood as an infinite sphere. The infinite sphere was geometrically determined only from the center, that is from any point, by three radii at right angles to one another. An infinite sphere was regarded as entirely similar in all its physical properties to a finite sphere. The question of the non-correspondence of geometrical, that is of Euclidean, three-dimensional space, whether finite or infinite, on the one hand, with physical space on the other hand, arose very occasionally and did not interfere with the development of physics in the directions that were possible to it. It was only about the end of the 18th and the beginning of the 19th century that the idea of this non-correspondence, the doubts as to the correctness of identifying physical space with geometrical space became so insistent that it was no longer possible to pass them over in silence. This doubt was aroused first by attempts at a revaluation of geometric values, that is, attempts either to prove the axioms of Euclid, or to prove their incorrectness. Secondly, by the very development of physics, or more exactly of mechanics, that is the part of physics dealing with motion. For this development led to the conviction that physical space could not be housed in geometrical space, and continually reached beyond it. Geometrical space could be taken as physical space only by closing one's eyes to the fact that in geometrical space everything is immovable. That it contains no time necessary for motion, and that the calculation of any figure resulting from motion, such as a screw for example, or a helical spiral, requires 4 coordinates and not 3. Later, the study of the phenomena of light, electricity, and the structure of the atom necessitated a similar broadening of space. The result of purely geometrical speculation concerning the correctness or incorrectness of the axioms of Euclid were twofold. On the one hand, a conviction arose that geometry was a purely speculative science, dealing solely with principles and entirely completed, that could neither be added to nor altered. Also a science which could not be applied to all the facts that are met with, that is true only under certain definite conditions, but within those conditions it is perfectly reliable and irreplaceable by anything else. On the other hand, there arose a certain disappointment in the geometry of Euclid, and a desire to remodel it. To rebuild it on a new basis, broaden things, and make it a physical science, that could be applied to all the facts that are met with, without the necessity for arranging these facts in an artificial order. This second attitude can be said to have triumphed in science and thus considerably delayed its development. Immanuel Kant's ideas of categories of space and time, taken as categories of perception and thought, have never entered into scientific, i.e. into physical thought, in spite of the various attempts later to introduce them within the compass of physics. Scientific, physical classical thought proceeded apart from philosophical and psychological, romantic thought. Scientific thought always took time and space as having an objective existence outside of us, and in virtue of this it was always considered possible to express their relations mathematically. However, the development of mechanics and other branches of physics led to the necessity for recognizing a fourth coordinate of space in addition to the 3 fundamental coordinates, i.e. length, breadth, and height. The idea of the fourth coordinate, or the fourth dimension of space, gradually became more and more inevitable, though for a long time it remained taboo. The material for the construction of new hypotheses of space remained in the works of mathematicians, Gauss, Lobachevsky, Sachet, Belai, and particularly Riemann, who in the latter half of the 19th century was already considering the question of the possibility of a totally new understanding of space. There were no serious attempts at a psychological study of the problem of space and time. The idea of the fourth dimension remained for a long time shelved, and by specialists was regarded as purely mathematical, by non-specialists as mystical or occult. However, if we start from the moment of the appearance of this idea, at the beginning of the 19th century, then make a brief survey of the development of scientific thought from that moment onward, it may help to understand the course that the further development of this idea might take. At the same time, we can see what this idea tells us or can tell us, with regard to the fundamental problem of the form of the world. The first and essential question that arises at this point is that of the relation of the physical sciences to mathematics. From the ordinary point of view, it is taken as fact that mathematics studies the relation of quantities in the same world of things and phenomena that are studied by the physical sciences. From this follow 2 more propositions. First, that every mathematical proposition must have a physical equivalent, though it may yet be undiscovered at the given moment. Then second, that every physical phenomenon can be expressed mathematically. In reality, neither of these propositions have any foundation, and the acceptance of them as axioms arrests the progress of thought, along the very lines where progress is most needed. In all further discussion of the physical sciences we can examine only physics proper. Then in physics we shall pay most attention in the beginning to mechanics, for since about the middle of the 18th century mechanics had assumed a predominant position in physics. So much so that until fairly recently it was considered both possible and probable that a means would be found of interpreting all physical phenomena as mechanical phenomena, that is, as phenomena of motion. Some scientists went even further and, not content with admitting the possibility of finding a means of interpreting physical phenomena as phenomena of motion, asserted that this means had already been found. That it explained not only physical phenomena, but also phenomena of life, and psychic phenomena. One often met with a division of physics into old and new, and in its chief lines this division can be accepted, but it should not be understood too literally. We can look at the fundamental ideas of old physics that led to the necessity for building new physics, and which unexpectedly destroyed old physics. Then come to the idea of new physics that led to the possibility of building a new model of the universe, which destroys new physics just as new physics destroyed old physics. Old physics lasted until the discovery of the electron. However, even the electron was conceived by old physics as existing in the same artificial world, governed by Aristotelian and Newtonian laws in which it studied visible phenomena. In other words, the electron was accepted as existing in the same world in which our bodies and other objects, commensurably with them, exist. Physics simply did not understand that the electron belongs to another world. Old physics was based upon certain immovable foundations. The space and time of old physics possessed very definite properties. First of all, they could be examined and calculated separately, i.e. the being of a thing in space in no way affected or touched upon its being in time. Furthermore, there was one space for all that exists, and all that occurred in this space. Time also was one for all that exists and was measured always and for everything by one scale. In other words, it was considered possible for one to measure all movements possible in the universe. The cornerstone of the whole understanding of the laws of the universe was the principle of Aristotle, concerning the unity of laws in the universe. This principle, in its modern meaning, can be formulated in the following way. In the whole of the universe and under all possible conditions, the laws of nature must be identical. In other words, a law that has been established in one place in the universe must hold good at any other place in the cosmos. On the basis of this, science, in studying phenomena on the Earth and in the solar system, assumed the existence of the same phenomena on other planets and in other solar systems. This principle, attributed to Aristotle, was in reality never conceived by him in the form it has acquired in our time. The universe of Aristotle differed greatly from the universe as we conceive it. The thinking of the people of Aristotle's time differed greatly from the thinking of the people of our time. Many fundamental principles, and many starting points of thought that we can accept as already established, had to be proven and established by Aristotle. Aristotle endeavored to establish the unity of laws in the sense of a protest against superstitions, against naive magic, against naive miracles, and against paganism. In order to understand the principle of Aristotle, it is necessary to understand that he had still to prove that if in general dogs cannot speak in human language, then say one particular dog in the island of Crete also cannot speak. If in general trees cannot move of themselves, then one particular tree also cannot move, and so on. All this has of course been forgotten long ago, and from the principle of Aristotle there follows now the idea of the permanency of all physical concepts such as motion, velocity, force, and energy. This means that what had once been regarded as motion always remains motion. What had once been regarded as velocity always remains velocity, simply becoming infinite velocity. In its first meaning, the principle of Aristotle is comprehensible and necessary, and is nothing other than the law of the general consecutiveness of phenomena that belongs to logic. But in its modern meaning, the principle of Aristotle is entirely wrong. Even for new physics, the concept of infinite velocity that is exclusively based upon the principle of Aristotle has become impossible, and the principle of Aristotle must be completely abandoned before the planning of a new model of the universe becomes possible. In speaking of physics, it is first of all necessary to analyze the very definition of the subject. According to the definition of textbooks, physics studies matter in space, and phenomena in this matter. Here we are immediately faced with the fact that physics operates with undefined and unknown quantities, that for the sake of convenience, or owing to the difficulty of definition, are taken as known quantities, and even as quantities requiring no definition. There are formally distinguished in physics, quantities requiring definition and primary quantities, the idea of which are considered to be inherent in all people. Primary quantities do not require definition, for their meaning is clear to everyone. The properties of these quantities are determined by the idea that everyone connects with their name, and therefore everyone should look in themselves for the identification of their properties. Professor O.D. Cholson, in his textbook on physics, 5th edition, published by Z.I. Gershobin, Berlin in 1923 refers to primary quantities. Extensions, linear extension, area extension, and volume extension, that is the length of a straight line, the area of a portion of surface, and the volume of a portion of space limited by surfaces. Extension, being the measure of size and of distance. Time, velocity of uniform rectilinear motion. These are only examples, and Professor ch41 does not insist on the completeness of the list. Unfortunately, the list is actually very long, as it includes space, infinity, matter, motion, mass, and so on. In a word, all the concepts with which physics operates. The profusion of undefined and undefinable quantities is the main characteristic of old physics. In a great many cases it is of course impossible to avoid operating with unknown magnitudes, and it became the traditional scientific method not to recognize anything unknown. To regard the quantities that entirely eluded definition as universally understood quantities, the idea of which was inherent in everyone. The natural result was that the whole of the vast edifice that had been erected with such tremendous labor, became artificial and unreal. In the definition of physics given, we meet with two undefined concepts, space and matter. Professor ch41 writes with regard to matter. In objectifying the cause of a sensation, that is transferring this cause into a definite place in space, we conceive this space as containing something, which we call matter or substance. Further, Professor ch41 writes, the use of the term matter was reserved exclusively for matter, which is able to affect our organ of touch more or less directly. Later, matter is then divided into organized matter, of which living bodies and plants are composed, and non-organized matter. This method of division, instead of definition, is applied in physics whenever definition is difficult or impossible, that is in relation to all fundamental concepts. The difference between organized matter and non-organized matter are determined only by external characteristics. The origin of organized matter is admitted to be unknown. Although the transition of non-organized matter into organized matter may be observed, i.e., feeding or breathing, it is admitted that such a transition only takes place in the presence, and through the action of already existing organized matter. The mystery of the first transition remains hidden, per ch41. On the other hand, we see that organized matter easily passes into non-organized matter, losing certain undefinable properties that we call life. Many attempts have been made to regard organized matter as a particular case of non-organized matter, and to explain all the phenomena that take place in organized matter, i.e. the phenomena of life as a combination of physical phenomena. However, these attempts, and also the artificial creation of organized matter from non-organized matter, led to nothing and could neither create nor prove anything. In spite of this, they left a strong impression on the philosophies of life of a scientific kind, from the standpoint of which the artificial creation of life is recognized as not only possible, but already partially attained. Followers of these philosophies regard the very name of organic chemistry, i.e. chemistry studying organized matter, as having only historical meaning, and define it as the chemistry of hydrocarbons. Although at the same time they cannot help admitting the special position of the chemistry of hydrocarbons, and its difference from general inorganic chemistry. Non-organized matter is in its turn divided into simple matter, and composite matter, which becomes the province of chemistry. Composite matter consists of a so-called chemical compound of several simple matters. Every matter can be divided into very small parts called particles. A particle is the smallest quantity of given matter that is still capable of exhibiting at least its chief properties. The further divisions of matter into molecule, atom, electron, photon, quark, and so on, are so small that taken separately, they do not possess any material properties. Though this last fact is rarely adequately taken into account. According to recent scientific ideas, non-organized matter consists of 92 elements, or simple matters, though not all of them have as yet been discovered. There exists a hypothesis that the atoms of various elements are nothing but a combination of a certain number of atoms of hydrogen, which in this case are taken as fundamental or primary matter. Several theories exist concerning the possibility or impossibility of the transition of one element into another, and in some cases such a transition has been established, which again contradicts the principle of Aristotle. Organized matter or hydrocarbons consist of 4 elements: hydrogen, oxygen, carbon, and nitrogen, with a negligible admixture of other elements. Matter possesses many properties, such as mass, volume, density, etc., which are in most cases definable, one relative to the other. The temperature of a body is recognized as depending upon the motion of molecules. Molecules are considered to be in perpetual motion. As physics defines it, they are constantly colliding and scattering in all directions, and then returning again. The greater the motion, the greater the shocks when they collide, and the higher the temperature or Brownian movement. If this were possible in reality, it would mean that, for example, several thousand automobiles, moving swiftly in different directions through a large city, crash into one another every minute, and then disperse again in different directions, remaining intact all the while. A speeded-up film, showing the movement of traffic in busy city streets, produces such an illusion. Rapidly moving objects lose their individuality, and appear to collide, then fly off in different directions, or even to pass through one another. How it can be that material bodies possessing mass, weight, and very complex structure, moving at great velocity, can collide and scatter without being broken up and destroyed is not explained by physics. One of the important conquests of physics was the establishment of the principle of the conservation of matter. This principle consists of the recognition of the fact that matter is never and in no physical conditions created anew, nor does it disappear. Its total amount remains constant. With the principle of the conservation of matter are connected the principles, established later, of the principle of the conservation of energy, and the principle of the conservation of mass. Mechanics is the name given to the science of motion of physical bodies, and of the causes upon which the character of this motion may depend in various cases, per ch also. However, as is the case of all other physical concepts, motion is not defined by physics. Physics only establishes the properties of motion, duration, velocity, and direction in space, without which properties a phenomenon cannot be called motion. The division and sometimes the definition of these properties take the place of the definition of motion, and the established characteristics of the properties are referred to motion itself. Thus motion is divided into rectilinear and curvilinear, continuous and non-continuous, accelerating and retarding, uniform and variable. The establishment of the principle of the relativity of motion led to a whole series of conclusions. The question then arose: if the motion of a material point can be determined only by its position in relation to other bodies or points, then how is the motion to be determined if the other bodies or points are also moving? This question became particularly complicated when it was established, not merely philosophically but scientifically, with calculations and diagrams, that nothing is motionless in the universe. That everything without exception moves in one way or another, and that one motion can be established only relative to another. At the same time, there were established cases of apparent immobility in motion. Thus it was established that separate component parts of a uniformly moving system of bodies maintain the same position in relation to one another as though the system were stationary. Thus things in a swiftly moving passenger airliner, moving at speeds of above Mach 1, behave in exactly the same way as when the aircraft is stationary. Then in the case of two or more moving systems of bodies, for instance, in the case of two transatlantic aircraft flying either in the same or in different directions, it was established that their relative velocity is equal to the difference between or the sum of their respective velocities, according to the direction of their movement. Hence two aircraft approaching one another will approach with a velocity equal to the sum of their respective velocities. For one aircraft overtaking another, the second aircraft will fly in a direction opposite to its own, with a velocity equal to the difference between the respective velocities of the two aircraft. What is usually called the velocity of an aircraft or body is the velocity that is ascribed to the aircraft during its passage between two objects which are stationary for it, for example between two cities and so on. The study of motion in general, and of vibratory and undulatory movements in particular, exercised a tremendous influence on the development of physics. Wave movements began to be regarded as a universal principle, and many attempts were made to reduce all physical phenomena to vibratory movements. One of the fundamental methods of physics was the measurement of quantities. The measurement of quantities was based upon certain principles, the most important of which was the principle of homogeneity. Namely, quantities conforming to the same definition, and differing from one another merely quantitatively, were called homogeneous quantities, and it was considered possible to compare them and measure one in relation to the other. As to quantities that differed in definition, it was considered impossible to measure them in relation to one another. Unfortunately, there were very few definitions of quantities in physics, and therefore definitions were generally replaced by their denominations. However, as mistakes in denomination can always occur, and qualitatively different quantities could be named similarly, while qualitatively identical quantities could be named differently, physical measurements were unreliable. Once again, the principle of Aristotle was felt, that is, a quantity once recognized as a quantity of a certain order, always remained a quantity of that order. Different forms of energy passed into one another, matter passed from one state to another, but space, or a part of space always remained space, time always remained time, motion always remained motion, velocity always remained velocity, and so on. On these grounds it was agreed to regard as incommensurable only those quantities that were qualitatively different. Quantities that differed merely quantitatively were regarded as commensurable. Continuing the subject of the measurement of quantities, it is necessary to point out that the units of measure used in physics are quite arbitrary, and have no connection with the quantities that are measured. All the units of measure have only one thing in common: they are always borrowed from elsewhere. There is not a single case in which a characteristic of a given quantity is taken as the measure. The artificiality of measures in physics has never been a secret, and from the realization of this artificiality follows attempts to establish, for instance, the measure of length as a part of the meridian. These attempts, though alter nothing, and parts of the human body, an ell or a foot taken as units of measure, or a meter, i.e. part of the meridian, are equally arbitrary. In reality, things bear their own measure in themselves. To find the measure of things is to understand the world. Physicists have dimly guessed this, though they have never succeeded in even approaching these measures. Professor Planck in 1900, which really belongs to new physics, constructed a system of absolute units. Taking as its basis universal constants, namely first, the velocity of light in a vacuum. Second, the constant unit of gravitation. Third, a constant quantity that plays an important part in thermodynamics, energy divided by temperature. And fourth, a constant quantity that is called action, energy multiplied by time, and is the smallest possible quantity of action, or its atom. Using these quantities, Planck obtained a system that he considered to be absolute, and entirely independent of any arbitrary choice of man, which he regarded as natural. Planck affirmed that the quantities would retain their natural meaning as long as the laws of universal gravitation and of the propagation of light in a vacuum, and the two fundamental principles of thermodynamics, remain unchanged. They will always be the same by whatever intelligent beings, or by whatever methods they are determined. However, the law of universal gravitation and the law of the propagation of light in a vacuum are the two weakest points in physics, because in reality they are not what they are taken for, therefore rendering Planck's entire system of measures unreliable. What is interesting in it, however, is not the result, but the principle, i.e. the recognition of the necessity for finding natural measures of things. The actual determination of absolute units of measure lies beyond the new model of the universe.